Hi, so in this video, we're going to talk about a different collision resolution strategy called quadratic probing. So we saw that in linear probing, it has the tendency to cluster. And the reason for that is when it looks for the next available bucket, it literally only looks at the bucket right next to it. So one way to kind of spread things out is, we can actually skip a bucket. We can look at every other bucket. Or how about we can skip, three buckets at a time. That in an effort to try to spread things out. Now, even better though. So instead of just skipping always a constant number of buckets, we can skip an increasing number of buckets to really spread things out. And so one of the way to do that is called quadratic probing. So in order to understand that, let's look back at this formula that we have previously, that a bucket index is the hash of the key modulo by the number of buckets. So with any sort of open addressing scheme, what we effectively are doing is that we add an additional probing function. It's called as f of k to this formula. So here, we insert f of k. Now, in the very first time, when k equals 0, this most likely is just going to return 0. So we are just looking at, the first bucket that the key is hashed to. Now, if that bucket is occupied, then, k becomes 1. This would give us a different number, and we probe the next location. And then if that location is still occupied, then this, k equal to 2, and we probe a different location, so on and so forth. So what happens with linear probing is that f of k is basically just k, right? So the first beyond the original location, we would just add 1 to the hash key, and then add 2 to the hash key, 3 to the hash key, and then continue from there until we find an available bucket. Now, for the new probing scheme, the quadratic probing, what f of k is k squared. So what that means is, when k is 1, then it's just plus 1, the same as before. However, when k is 2, now we're skipping a few more locations. We go to, hash key plus 4, and we still cannot find it. Then we go to the next one, k equal to 3, and then the location we're looking at would be 9 buckets away. So that's quadratic probing in a nutshell. It's very similar to linear probing other than the f of k. So let's take a look at how it works in practice. So same example as before, we're inserting 49 and 16. You know how that works. Now the next thing we do, okay, let's insert number 7. So number 7, again, initially we just plus 0 modulo by 7. It hashed to this bucket 0. We've seen that, and that's occupied. So the next number we add, the next position, we just add 1. 1 square is 1. So that's one. We put it here. So nothing has changed so far. Now the interesting thing is, okay, what happens when we want to insert 14? 14, if you see the f of k here, it goes from 0 to 1 to 4. So, and we know at position 0 and 1, it's already occupied. However, at position 14 plus 4, that's 18 modulo by 7, that is position 4 in the case of quadratic probing. And if you remember from linear probing, we actually ended up here instead of position 4. Okay, so that's kind of how it works. And now it's your turn to try to insert the number 21 and see what happened. And I promise this is going to be a fun one. So you really, really want to try this one. So assuming you have tried this, you'll find it kind of strange because you actually cannot find a bucket to insert the number 21. I don't know how far you've gone. Here I calculated k from 0 all the way up to 15. using a spreadsheet. And the bucket index, as you can see, it kind of cycles between 0, 1, 2, and 4, and 0, 1, 2, and 4, they are all occupied. So what actually happened here? Well, the problem is the load factor. And the load factor in this case is 4/7, and that happens to be greater than 0.5. So there is actually a theorem that says if you are using open addressing hash table of a prime size, and if you're using quadratic probing, then you're guaranteed to find an empty bucket if the load factor is less than 0.5. However, in our case here, it's bigger than 0.5. That's why we could not find an empty bucket. Now, there is a little nice proof that's linked from the readings. So I replicate the URL here. Feel free to read it, try to understand it on your own, but it's optional. So what this actually says is for quadratic probing to work, we have to always keep half of the table empty. That's all good. The only problem is obviously we are wasting a little bit of space. Well, actually half of the space, which I mean it could be acceptable in depending on your application. Now, so let's think about the performance a little bit, and actually the open addressing hash table in general. So on average, it's actually very similar to other hash tables, and it should be out of 1, right? Assuming, again, you have a good hash function. In the worst case, though, it's still out of n, because what happens what if there are just a lot of collisions and we just have to search through everything to find anything, right? So in that regard, it's really no different from any other hash table. So again, moral of the lesson is we need good hash functions for any kind of hash table.